Hello there, and welcome to the Sleepy Library. It's lovely to have you here. Before we begin, I'd love to know, where in the world are you watching from tonight? Perhaps you're nestled under warm blankets, or sitting by a window watching the evenings settle in. Or maybe you're somewhere in between waking and dreaming already. Wherever you are, I hope you're comfortable, safe, and ready to gently explore something ancient and wonderful. If you enjoy these relaxing journeys through science and would like to hear more, a like and subscribe really helps this channel continue. And to those of you already subscribed, thank you. Your support means more than you know. Now, let's begin our quiet journey into the past, written in the oldest books on Earth. Have you ever held a stone in your hand and wondered about its story? That smooth pebble you picked up from a beach, or that rough rock from a mountain trail? These aren't just lifeless lumps of minerals. They're pages from Earth's diary, carefully preserved over millions, sometimes billions of years. Every stone you've ever touched has witnessed moments you can barely imagine. Ancient oceans that no longer exist, volcanoes erupting under skies that held different stars, creatures that walked the earth long before humans ever dreamed of writing history. Tonight, we're going to slow down and listen to what the rocks have to say. We'll learn how Earth keeps its diary, how every layer and color and crack holds a story about volcanic eruptions, ancient oceans, and life itself. We'll discover that stones aren't silent at all. They're whispering constantly about where they came from, what they've seen, and how our planet has changed over unimaginable stretches of time. So, settle in, close your eyes if you'd like, and let's drift together through billions of years of Earth's history, all recorded in the stones beneath our feet. Imagine Earth as a writer, one who has been keeping a journal for over 4.5 billion years. But this writer doesn't use pen and paper or even words. Earth writes in rock. Every stone, every layer, every tiny crystal is a page in this vast, ongoing diary. And unlike books that crumble or ink that fades, these pages can last for billions of years, patiently waiting for someone to read them. When you look at a cliff face with its stripes of different colored rock, you're looking at chapters of Earth's autobiography. The bottom layers are the oldest sentences, written when our planet was young. The top layers are more recent, recording events that happened just millions of years ago, which in Earth time is practically yesterday. Each layer tells us something different about what was happening when that rock was made. Some layers speak of quiet times, when gentle rivers carried sand grain by grain to settle at the bottom of ancient seas. Other layers shout of drama, of mountains being born, of continents colliding like slow-motion car accidents, of fire and pressure transforming everything they touch. Earth's diary isn't neat or organized like human books. There are pages missing, torn out by erosion. There are sections where new chapters were written right over old ones, mixing up the timeline. But with patience, scientists have learned to read this rocky language, and the stories they've uncovered are breathtaking. Think of it this way. If you wanted to understand your grandmother's life, you might look at her photo albums, read her letters, examine the things she kept. Earth's rocks are like that. They're the physical evidence of what our planet has experienced. A volcano's eruption becomes frozen lava. An ancient sea becomes limestone packed with tiny shells. A forest buried by mud becomes coal, compressed over millions of years. Every time you step outside, you're walking on history. The sidewalk beneath your feet might contain rocks that were once at the bottom of an ocean. The mountain in the distance might have been built by two continents pushing against each other for millions of years. The beach sand might be made from mountains that were once taller than any we see today, slowly worn down grain by grain over countless centuries. What makes rocks such good record keepers is their patience. They don't forget. A volcanic eruption might last for days, but the rock it creates can remember that brief, violent moment for hundreds of millions of years. A single season of winter, when ice formed patterns in mud, can be preserved perfectly, like a photograph in stone. Earth's diary is written in a language that lasts, and tonight we're going to learn how to read some of its most beautiful passages. So, let's begin with the basics. Let's meet the three types of rocks that make up Earth's autobiography, each one telling its own kind of story, each one holding its own secrets about our planet's incredible past. Now, if Earth were writing chapters about its life, it would need different types of pages for different types of stories. And that's exactly what we find. Rocks come in three main types, and each one forms in a completely different way, recording completely different moments in Earth's history. Think of them as three different chapters in Earth's endless book. There are rocks born from fire, rocks built from tiny pieces over time, and rocks transformed by pressure and heat. Each has something unique to tell us. Let's start with the rocks born from fire. These are called igneous rocks, from the Latin word for fire, and their story begins deep, deep underground, or sometimes shooting spectacularly into the sky. Deep beneath your feet, even as you rest comfortably now, Earth's interior is incredibly hot. So hot that rock itself melts into a thick, glowing liquid called magma. Think of it like Earth's secret kitchen, hidden miles below the surface, where ingredients are melted and mixed at temperatures that would turn any ordinary rock into glowing soup. This magma is restless. It wants to rise too, move toward the surface where it's cooler. Sometimes it makes the journey slowly, creeping through cracks in the Earth's crust, cooling down gradually over thousands or even millions of years as it travels. When magma cools slowly like this, deep underground, something special happens. The minerals inside have plenty of time to organize themselves into beautiful, visible crystals. It's like giving sugar time to form rock candy, rather than just dissolving instantly. The result is rocks with large, distinct crystals that you can see with your naked eye. Granite is one of these rocks. If you've ever seen a granite countertop or a granite mountain, you've seen those little sparkles and specks. Those are crystals of different minerals, like quartz and feldspar, all locked together in a mosaic that took thousands of years to form. But sometimes magma doesn't wait. Sometimes it bursts forth in a spectacular display, erupting from volcanoes as lava. When this happens, the story changes completely. The molten rock suddenly finds itself in the cool air or ocean water, and it freezes almost instantly, geologically speaking. There's no time for large crystals to form. Instead, the rock solidifies so quickly that its crystals are tiny, sometimes too small to see without a microscope. Basalt is one of these rocks. It's dark, it's fine-grained, and it's everywhere. The ocean floor is mostly basalt. Volcanic islands are built from basalt. Some of it even forms strange, beautiful columns as it cools and cracks in geometric patterns. One of the most dramatic examples of fast-cooling lava is obsidian, also known as volcanic glass. It cools so quickly that crystals don't have time to form at all. Instead, the atoms freeze in place in a random arrangement, creating a smooth, glassy surface that can be sharper than any steel blade. Ancient peoples used obsidian to make cutting tools because it could hold such a fine edge. Each piece of obsidian is a snapshot of a moment, a split second when fire met air and froze into black, glassy beauty. Igneous rocks are Earth's way of saying, "Look what I can do with fire and time." They tell us about the planet's internal heat, about volcanic eruptions ancient and recent, about mountains being built and islands being born. When you hold a piece of granite, you're holding something that formed in Earth's secret kitchen, slowly crystallizing in the darkness far below. When you hold basalt, you're touching the surface of ancient lava flows, frozen mid-journey as they raced down volcanic slopes. But fire is only one way Earth writes its diary. Let's turn to a gentler chapter, one written not in explosive moments, but in quiet patience over millions of years. If igneous rocks are Earth's dramatic volcanic stories, then sedimentary rocks are its patient, layered memories. These rocks aren't born from fire. They're built, piece by tiny piece, like a very slow construction project that takes millions of years to complete. Imagine a library where books are made not by writing words, but by carefully stacking one grain of sand at a time, year after year, century after century, until those grains become pages, and those pages become chapters. Sedimentary rocks begin with something simple, the breaking down of older rocks. Wind, rain, ice, and flowing water are constantly, tirelessly working to wear down mountains, cliffs, and boulders. A raindrop might seem harmless, but millions of raindrops over thousands of years can dissolve rock. Frost can crack stone apart. Rivers can carry away tiny fragments. This process is called weathering, and it never stops. Right now, somewhere in the world, a mountain is being slowly dismantled, grain by grain. These tiny pieces, these fragments of what used to be larger rocks, are called sediment. They might be pebbles, or grains of sand, or particles so small you need a microscope to see them. These sediments get carried away by water, by wind, by glaciers. They travel sometimes for miles, sometimes for just a few feet, and eventually they settle somewhere. They might sink to the bottom of a lake, or drift to the floor of an ocean, or pile up at the mouth of a river. As more and more sediment accumulates, something remarkable happens. The weight of the newer layers presses down on the older layers below. This pressure squeezes the grains together. Water that was trapped between the grains gets pushed out, and slowly, very slowly, minerals dissolved in that water act like natural glue, cementing the grains together. What was once loose sand becomes sandstone. What was once mud becomes shale or mudstone. What were once tiny shells and coral fragments become limestone. This process can take thousands to millions of years, but the result is worth the wait. Sedimentary rocks are like time capsules. Each layer represents a different moment in Earth's past. A layer of sandstone might tell us about an ancient beach, where waves once rolled in and out, leaving their patterns in the sand. A layer of shale might speak of a quiet, muddy sea floor, where nothing disturbed the settling sediment for thousands of years. A layer of limestone might be packed with the shells of countless tiny sea creatures, each one adding its tiny contribution to the growing stone. One of the most beautiful things about sedimentary rocks is their layers, sometimes called beds or strata. When you see a cliff with horizontal stripes of different colors, you're looking at different layers, each one representing a different time period. The bottom layer is the oldest, like the first page in a book. The top layer is the youngest, like the last page written. In between, you can sometimes read the history of hundreds of millions of years. These layers can tell us amazing things. A red layer might mean that the sediment was exposed to oxygen, perhaps on land. A black layer might mean it formed in deep water where there was no oxygen. A layer with ripple marks tells us that waves or currents were moving over the sand when it was still wet. A layer with cracks tells us it dried out, perhaps during a time when the sea level dropped or when a lake evaporated. But sedimentary rocks hold something even more precious than colors and patterns. They hold fossils. Because sedimentary rocks form from layers of sediment that pile up gradually, they sometimes bury things. And if those buried things are the remains of plants or animals, and if the conditions are just right, those remains can be preserved for millions of years. We'll talk more about fossils later, but for now, just know that sedimentary rocks are Earth's main archive for ancient life. Think of sedimentary rocks as Earth's gentle memory. They're not formed in dramatic explosions or intense heat. They're formed slowly, peacefully, layer by layer, like snowflakes accumulating during a quiet winter. But over millions of years, those quiet accumulations tell some of the most detailed stories we have about Earth's past. Limestone, in particular, is one of the most fascinating sedimentary rocks. Most limestone forms from the tiny shells and skeletons of countless marine creatures. When these organisms pass away, their hard parts, made of calcium carbonate, sink to the ocean floor. Over time, these fragments pile up, get compressed, and become solid rock. When you look at limestone, you're looking at what used to be life itself, transformed into stone. Some limestone is so full of shells and coral that you can see the individual shapes, like a graveyard of ancient sea life turned to stone. Sedimentary rocks also include some unusual characters. Coal, for example, is a sedimentary rock made from the compressed remains of ancient plants. Millions of years ago, vast, swampy forests grew, flourished, and then sank beneath layers of mud and sediment. Under all that pressure, the plant material slowly transformed into coal. Every piece of coal you see began as green, living plants in a forest that existed long before humans walked the earth. And then there's chalk, a special type of limestone made from the shells of microscopic organisms called coccolithophores. These tiny creatures lived in ancient seas, and when they passed on, their microscopic shells drifted down and accumulated on the seafloor. Over millions of years, those accumulations became the white cliffs you can see in places like Dover, England. When you write with a piece of chalk, you're using the compressed remains of countless tiny creatures that lived hundreds of millions of years ago. Sedimentary rocks teach us patience. They remind us that even the gentlest processes, repeated over enough time, can create something grand. A single grain of sand is almost nothing, but 1 trillion grains of sand, compressed over 1 million years, can become a cliff that stands for millions more. That's the quiet magic of sedimentary rocks. They turn time itself into stone. But Earth's diary isn't complete with just fire, patience. There's a third type of rock, one that tells a different story altogether, a story of transformation. Now we come to the rocks that have been rewritten, the pages that Earth took back and changed, like an author editing an old draft. These are called metamorphic rocks, and their name comes from Greek words meaning change of form. These rocks started as something else, either igneous or sedimentary rocks, but then something happened to them. They were buried deep or caught in the collision of continents or baked by nearby magma. And under all that heat and pressure, they changed. They transformed into something new, like a caterpillar becoming a butterfly, but made of stone. Imagine taking a piece of clay and squeezing it hard in your hands. It changes shape, but it's still clay. Now imagine squeezing that clay while it's also being heated. The minerals inside might start to rearrange themselves, forming new patterns, new structures. That's a bit like what happens when sedimentary or igneous rocks get buried deep in the Earth's crust, or caught between colliding tectonic plates. The pressure can be immense, like having miles of rock pressing down from above. The temperature can be incredibly hot, though not quite hot enough to melt the rock completely. If it melted, it would become magma, and eventually an igneous rock. But metamorphic rocks stay solid throughout their transformation. The minerals just rearrange themselves, like shuffling a deck of cards without changing the cards themselves. One of the most common metamorphic rocks is slate. Slate starts its life as shale, a soft sedimentary rock made from mud. But when shale gets buried and squeezed, the clay minerals inside start to align, all facing the same direction, like soldiers standing at attention. This alignment makes slate split easily into thin, flat sheets. For centuries, people have used slate as roofing material because of this property. Every slate roof is made from mudstone that was transformed by pressure deep underground. If you squeeze slate even more, with even more heat and pressure, it transforms again into phyllite. Phyllite has a silky sheen to it, a slight sparkle that catches the light. The minerals are still aligning, still organizing themselves. Push it further still, and phyllite becomes schist. Schist is coarser, with visible grains of mica that give it a distinctive sparkle. Those sparkles are actually flat crystals of mica, all oriented the same way, reflecting light. It's beautiful in a way that only transformation can be. One particularly interesting metamorphic rock is marble. Marble starts as limestone, that rock made from ancient shells and coral. When limestone is heated and pressured, the calcite crystals inside grow larger and interlock, forming the smooth, crystalline texture we recognize as marble. Pure marble is white, but impurities in the original limestone can add streaks of color, grays, greens, pinks, creating the beautiful patterns that artists and architects have prized for thousands of years. Michelangelo carved his sculptures from marble. The Taj Mahal is clad in white marble. These masterpieces of human artistry are carved from stone that Earth itself had already sculpted deep underground. Another fascinating metamorphic rock is gneiss, pronounced nice. Gneiss often forms when granite, that speckled igneous rock, is subjected to heat and pressure. The minerals in granite separate into light and dark bands, creating a striped appearance. These bands, called foliation, tell a story of immense forces acting on the rock, stretching and squeezing it over millions of years. Some gneiss is incredibly ancient, among the oldest rocks on Earth, preserving memories of our planet's earliest days. Metamorphic rocks are Earth's way of saying nothing is permanent. They remind us that even stone can change, that given enough time, pressure, and heat, anything can transform into something new. They're like the edited pages in Earth's diary, where the original story is still there, but with new words written between the lines, new meanings layered on top of old ones. When you hold a piece of marble, you're holding ancient sea life that was transformed by heat and pressure into something beautiful. When you see the sparkle of schist, you're seeing minerals that reorganize themselves under the weight of mountains. Metamorphic rocks are Earth's poets, taking old stories and transforming them into something that feels entirely new. So now we've met all three types of rocks: igneous rocks born from fire, sedimentary rocks built slowly from pieces, and metamorphic rocks transformed by heat and pressure. Together, these three types of rocks contain all the chapters in Earth's diary. They work together in what scientists call the rock cycle, with igneous rocks being broken down into sediment, sediment being compressed into sedimentary rocks, and any rock, given enough heat and pressure, transforming into metamorphic rock. And any metamorphic rock, if it gets hot enough, can melt and become magma again, restarting the cycle. It's a beautiful loop, this rock cycle. It means that the atoms in any given rock might have been part of many different rocks before, cycling through fire and pressure and time, being written and rewritten in Earth's endless diary. The granite countertop in someone's kitchen might contain atoms that were once part of an ancient ocean, then part of a mountain, then melted deep underground before crystallizing again as granite. Every rock has a history that stretches back further than we can easily imagine. But rocks aren't just three types with simple stories. They also contain something even more precious and more specific. Something that brings Earth's past to life in the most literal way possible. Let's talk about the letters Earth writes in its diary, the photographs it preserves for millions of years. Let's talk about fossils. If rocks are the pages in Earth's diary, then fossils are the photographs, the detailed illustrations that bring those pages to life. A rock can tell you about ancient oceans or volcanic eruptions, but a fossil can show you exactly what was living in that ancient ocean, or what grew near that volcano. Fossils are time capsules of life itself, preserved in stone. But how does a living thing become a fossil? It seems almost magical that soft flesh and bone can turn into hard rock, that something as delicate as a leaf or a shell can last for hundreds of millions of years. The process is rare and special, requiring just the right conditions, like a perfect recipe that only occasionally comes together. It begins with something passing away, perhaps a fish in an ancient sea, or a leaf falling from a prehistoric tree, or a trilobite scuttling along the seafloor before coming to rest. For that organism to become a fossil, it needs to be buried quickly, before scavengers eat it or bacteria break it down completely. This quick burial usually happens in water, where sediment is constantly settling. A fish might sink into mud. A leaf might drift to the bottom of a lake and get covered by silt. A shell might be buried by a storm that stirs up sand. Once buried, the organism is protected from the outside world. Oxygen can't reach it, so decomposition slows down dramatically. Slowly, over thousands and millions of years, minerals from the surrounding water seep into the tiny spaces inside the bones or shell or wood. These minerals, often silica or calcite, fill in the microscopic pores like cement filling cracks. The original material might dissolve away entirely, but the minerals stay behind, creating a perfect stone replica of what was once alive. This process is called permineralization. Sometimes the original shell or bone remains, but more often, only its shape survives. The organism's remains create an impression in the surrounding sediment, like pressing your hand into wet concrete. If that impression fills with minerals, you get a cast, a perfect copy of the original shape. If the original material dissolves away completely, you're left with a mold, a hollow space in the rock that shows exactly where the organism once was. What's remarkable is how much detail can be preserved. Some fossils show individual cells in wood, or the delicate veins in leaves, or the tiny structures inside shells. Some show footprints, not the animal itself, but the exact mark it left in mud as it walked by millions of years ago. Some even preserve soft tissues in rare circumstances, like the occasional dinosaur fossil with skin impressions, or insects trapped perfectly in amber, the fossilized resin of ancient trees. Think about this for a moment. You can hold in your hand a shell that last opened and closed when dinosaurs walked the earth. You can see the exact pattern of veins on a leaf that photosynthesized sunlight before any flowers existed. You can trace the fossilized footprint of a creature that lived, breathed, hunted, and survived in a world so different from ours that we can barely imagine it. Fossils are not just rocks, they're connections to life across impossible spans of time. Fossils teach us what ancient life looked like. They show us the trilobites that scuttled across Cambrian seafloors 500 million years ago, with their segmented bodies and compound eyes. They show us the giant dragonflies with 2-foot wingspans that flew through Carboniferous forests 300 million years ago. They show us the ammonites, those beautiful spiral shells that filled Mesozoic oceans for hundreds of millions of years before going away at the same time as the dinosaurs. Speaking of dinosaurs, their fossils are perhaps the most famous of all. From tiny Compsognathus, no bigger than a chicken, to massive Argentinosaurus that might have weighed as much as 10 elephants, dinosaur fossils show us a world where reptiles ruled the land. Their bones, preserved in stone, tell us how they walked, what they ate, how fast they might have moved. Some fossils even preserve evidence of feathers, showing us that the connection between dinosaurs and modern birds isn't just a theory, it's written in stone. But fossils aren't just for dinosaurs. Some of the most abundant fossils are the remains of microscopic organisms, things so small you'd never notice them while alive. Foraminifera, tiny single-celled creatures with intricate shells, are found by the billions in some rocks. Their fossils help scientists understand ancient ocean temperatures and depths. Coccolithophores, those microscopic algae we mentioned earlier, make up entire cliffs of white chalk. Pollen grains, microscopically small, can be fossilized and identified, telling us what plants grew in an area millions of years ago. Plant fossils are particularly beautiful. Ferns, cycads, and conifers have left perfect impressions in stone. Some coal deposits contain fossilized bark and wood so well preserved you can count growth rings, like reading tree rings to determine the age of a living tree. In rare cases, entire forests have been preserved. The petrified forest in Arizona contains thousands of logs that turn to stone, their cellular structure so perfectly mineralized that you can still see the original wood grain, all painted in brilliant colors by different minerals. Then there are trace fossils, which don't show the organism itself, but evidence of its activity. Footprints are trace fossils. Burrows in ancient mud are trace fossils. Even fossilized droppings, called coprolites, are trace fossils that can tell us what ancient creatures ate. These traces are like diary entries written by the organisms themselves, accidentally preserved for us to find millions of years later. Every fossil is a small triumph over time. For every organism that becomes a fossil, millions more simply disappear without a trace. The fossil record is incomplete, like a book with most of its pages missing. But the pages that remain are precious beyond measure. They show us that life on Earth has been incredibly diverse, that species come and go, that what seems permanent is always changing. When paleontologists find a new fossil species, they're adding a new entry to Earth's encyclopedia of life. They're recovering a memory that had been lost. And every time you see a fossil in a museum or a book, or even in a piece of limestone in a building, you're looking at proof that life has been experimenting, adapting, and evolving for billions of years. You're seeing evidence that the Earth was never still, that it was always full of living things making their mark, leaving their traces, writing their brief stories in stone before the chapters closed. Fossils are Earth's way of preserving its former inhabitants, of keeping a record of life that once was. They're gentle reminders that we too are part of this ongoing story, that humans are just the most recent chapter in a book that began long, long before us, and will continue long after we're gone. They connect us to the deep history of life, making the past feel a little less distant, a little more real. But rocks don't just record life, they also record time itself, marking the passage of years, decades, and millennia in ways that we're only beginning to fully appreciate. Let's explore how rocks keep time, how they act as Earth's clocks. If you've ever counted the rings on a tree stump to determine its age, you already understand one way that nature keeps time. Each ring represents 1 year of growth. Well, rocks can do something similar, though the mechanism is different. There are layers in certain rocks that form annually, year after year, creating a timeline that scientists can read like a calendar, going back thousands or even millions of years. These annual layers are called varves, and they form in lakes and glacial environments where conditions change with the seasons. During spring and summer, when snow and ice melt, rivers carry a lot of sediment into lakes. This sediment is relatively coarse, made of sand and silt particles. It settles quickly to the lake bottom, forming a light-colored layer. But in fall and winter, when the water is calmer and sometimes covered with ice, only the finest particles, the tiny clay particles, can settle. These form a darker, thinner layer. Each pair of layers, one light and one dark, represents 1 year. It's like a bookmark in time, a physical record of Earth's rotation around the Sun. By counting these varves, scientists can construct precise chronologies going back tens of thousands of years. They can correlate varve patterns from different lakes, matching thick years with thin years, building regional and even continental timelines. Varves aren't just counters of years, they also tell stories about climate. A thick, light layer might mean a year with lots of snowmelt, perhaps a warmer or wetter year. A thin layer might mean a colder year with less melting. Patterns in varve thickness can reveal cycles of climate variation, helping scientists understand how Earth's climate has changed over time. But varves are just one way rocks mark time. Another time marker comes from dramatic events like volcanic eruptions. When a volcano erupts, it can spread a layer of ash over huge areas. This ash layer settles on top of whatever sediment is there at the time. Because volcanic eruptions happen relatively quickly, these ash layers mark a specific moment in time. They're like dated headlines in a newspaper saying, "This event happened at this particular point." Geologists use these volcanic ash layers to correlate rocks in different places. If you find the same distinctive ash layer in 2 locations, you know those 2 rock formations were deposited at around the same time, even if they're hundreds of miles apart. It's like finding the same photograph in 2 different history books and knowing they both describe the same period. Some ash layers are so distinctive and widespread that they've been given names. The Campanian ignimbrite, for example, is an ash layer from a massive volcanic eruption in Italy about 39,000 years ago. This ash spread across the Mediterranean and can be found in sediments throughout the region. When scientists find this layer, they know immediately they're looking at rocks from that specific time period. Beyond varves and ash layers, rocks keep time in even more subtle ways. Ice cores, drilled from glaciers and ice sheets, contain annual layers just like varves. Each year's snowfall adds a new layer, and air bubbles trapped in the ice preserve samples of the ancient atmosphere. Scientists have drilled ice cores in Antarctica that go back over 800,000 years, providing an incredibly detailed record of ancient temperatures and atmospheric composition. Even within a single rock layer, there can be smaller time markers. Ripple marks in sandstone can show the direction of ancient currents and even the strength of those currents. Mud cracks tell us that the mud was exposed to air and dried out, perhaps indicating a season of drought or a temporary drop in sea level. Crossbedding, where layers are tilted at angles within the main layer, shows us how sand dunes migrated or how river channels shifted over time. All of these features are like entries in Earth's daily planner. They mark specific moments and give us a sense of what was happening when the rock was forming. Was it a calm day or a stormy one? Was the water deep or shallow? Was it a time of abundant life or a time of scarcity? Rocks remember, and if we learn to read their language, they can tell us. The concept of deep time, the billions of years over which Earth has existed, can be hard for our minds to grasp. But rocks make it tangible. When you see varves stacked one upon another for thousands of layers, representing thousands of years, and then realize that this is just a tiny slice of Earth's history, start to feel the immensity of geological time. When you see sedimentary rocks with hundreds of layers, each layer representing perhaps thousands of years, stacked into cliffs that rise hundreds of feet, you're looking at millions of years of patient accumulation. Time markers in rocks remind us that Earth's story is long and detailed. Every year, every season, every day left some trace if we know where to look. Earth has been keeping careful records all along, writing its diary day by day, year by year, epoch by epoch. And we're only now learning how to read all the tiny notations, the subtle timestamps that Earth scattered throughout its rocky pages. These time markers are essential for understanding Earth's history. They help us put events in order, to know that this extinction happened before that climate change, that this ice age came after that volcanic event. They help us see patterns, cycles, and rhythms in Earth's past. And they connect us to time in a way that few other things can, reminding us that we're just visitors in a story that stretches far, far into the past, and will continue far into the future. But rocks don't just record life and time. They also record something unexpected, something almost invisible, yet incredibly powerful. They record the Earth's magnetic field and its remarkable history of flipping back and forth. Now let's talk about something truly fascinating and a little bit mysterious. Earth has a magnetic field, an invisible force that makes compass needles point north and protects us from harmful solar radiation. But this magnetic field isn't constant. Throughout Earth's history, it has flipped, with the north and south magnetic poles trading places. And remarkably, rocks remember these flips. They keep a record of Earth's magnetic past, frozen in stone. When igneous rocks form, as molten magma cools and solidifies, tiny magnetic minerals inside align themselves with Earth's magnetic field at that moment. It's like millions of tiny compass needles, all pointing the same direction, and then getting frozen in place as the rock hardens. These minerals, like magnetite and hematite, are naturally magnetic, and they respond to Earth's magnetic field just like a compass does. Once the rock is solid, those minerals stay aligned in that direction, creating what scientists call remnant magnetization. The rock has recorded the direction of Earth's magnetic field at the time it formed. Even if the magnetic field changes later, the rock remembers what it was like millions of years ago. It's like a photograph of an invisible force captured in stone. Now here's where it gets really interesting. When scientists started studying the magnetic orientation of rocks, they noticed something strange. Some rocks have magnetic minerals that point toward what we consider north. But other rocks, even ancient ones from the same location, have minerals that point the opposite way, toward what we consider south. At first, this seemed wrong, like the rocks were somehow confused. But then scientists realized something remarkable. The rocks weren't confused at all. Earth's magnetic field had actually reversed. This wasn't speculation or theory, it was written clearly in the rocks. At various times in Earth's past, the magnetic North Pole was in the south, and the magnetic South Pole was in the north. The entire planetary magnetic field flipped, like turning a bar magnet upside down. And then, after some time, it flipped back. And then it flipped again. And again. Earth's magnetic field has reversed hundreds of times over the last several 100 million years. These reversals don't happen quickly. They take thousands of years to complete, with the magnetic field weakening, becoming chaotic, and then reorganizing in the opposite direction. During a reversal, compasses might not point reliably north. The magnetic field would be weaker, offering less protection from cosmic radiation. It would be a strange and somewhat hazardous time. But eventually, the field stabilizes again, just in the opposite direction. The pattern of these reversals is recorded in rocks all over the world, but especially clearly in the rocks of the ocean floor. As new oceanic crust forms at mid-ocean ridges, where tectonic plates spread apart, magma rises, cools, and records the magnetic field at that moment. As the seafloor spreads, carrying this newly formed rock away from the ridge, more magma rises, cools, and records the current magnetic field. Over millions of years, this creates a striped pattern on the ocean floor. Stripes of normal polarity, matching today's field, alternate with stripes of reversed polarity, opposite to today's field. These magnetic stripes were one of the key pieces of evidence that confirmed the theory of plate tectonics. Scientists realized that the symmetric pattern of magnetic stripes on either side of mid-ocean ridges proved that new ocean floor was being created at these ridges and spreading outward. It was like a magnetic barcode of Earth's history, proving that the continents really do move, that the ocean floor is constantly being recycled, that Earth's surface is dynamic and ever-changing. But beyond proving plate tectonics, paleomagnetism, the study of ancient magnetic fields preserved in rocks, tells us other things too. By measuring the angle at which magnetic minerals are tilted in rocks, scientists can figure out the latitude where the rock formed. Magnetic field lines are steep near the poles and shallow near the equator. So, if you find a rock with steeply tilted magnetic minerals in what's now a tropical location, you know that rock formed much closer to a pole and has since moved to where it is today. This helps scientists reconstruct ancient maps, showing where continents were positioned millions of years ago. India, for example, used to be much farther south, down near Antarctica. Rocks in India show this, their magnetic minerals pointing to a latitude far from where India is today. Over tens of millions of years, India drifted north, eventually colliding with Asia and creating the Himalayas. The rocks recorded this entire journey in their magnetic signatures. Earth's magnetic field reversals also help scientists date rocks and correlate rock layers from different parts of the world. Because the pattern of reversals is the same everywhere on Earth, if you know the magnetic signature of a rock layer, you can match it to the global timeline of magnetic reversals and determine its age. It's like having a universal clock that all rocks share. There's something poetic about this. Earth's invisible magnetic field, generated by the swirling motion of molten iron in the planet's outer core, somehow imprints itself on solid rock. The rocks become memory keepers for a force we can't see or touch, but that shapes our entire planet. They tell us that Earth is more dynamic than we often realize, that even its most fundamental fields can change, can reverse, can rewrite themselves while leaving the old versions preserved in stone. When you hold an igneous rock, you might be holding a record of Earth's magnetic field from millions of years ago, a tiny frozen snapshot of an invisible force that once surrounded the planet. It's a reminder that rocks aren't just static objects. They're active records, constantly telling us things if we learn their language. Magnetism in rocks connects us to Earth's deep interior, to the swirling convection currents of liquid metal far below our feet. It connects us to the planet's protective shield, the magnetic field that deflects harmful solar wind and makes life on the surface possible. And it connects us to time, to the countless reversals that have happened over Earth's long history, each one recorded faithfully by patient stones. So rocks hold stories of fire, stories of ancient life, stories of time's passage, and even stories of invisible forces. But they also tell us about another crucial topic, one that affects us all today. They tell us about climate. Earth's climate has never been constant. Over billions of years, our planet has swung between ice ages and greenhouse warmth, between vast glaciers covering continents and tropical forests growing near the poles. And rocks remember all of it. They're our most detailed archive of ancient climates, telling us not just that the climate changed, but how, when, and why. Let's start with limestone again, that rock made from the shells and skeletons of marine organisms. Limestone forms primarily in warm, shallow seas. When you find limestone in a rock formation, you know that area was once under a warm ocean. But the type of limestone can tell you even more. Some limestone is made from coral reefs. Coral reefs only grow in tropical waters, warm and clear and relatively shallow. If you find ancient coral reef limestone in a place that's now cold, you know that place once had a tropical climate. Geologists have found coral reef limestone in places like Canada and Alaska, far north of where coral grows today. This tells us that millions of years ago, these northern regions were much warmer, that the climate then was very different from now. Similarly, coal deposits tell us about ancient climates. Coal forms from the remains of plants that grew in swampy forests. When you find coal, you know that area was once warm and wet enough to support lush vegetation. Coal deposits in Antarctica, now a frozen desert, tell us that Antarctica once had a temperate climate with abundant plant life. Glacial deposits also record climate. When glaciers move across the land, they scrape and grind the rock beneath them, creating distinctive scratches called glacial striations. They also leave behind unsorted piles of rocks and sediment called till. When geologists find glacial till and striations in rock formations, they know a glacier passed through. The distribution of these glacial deposits shows us the extent of ancient ice ages, revealing that ice sheets once covered areas that are now temperate or even warm. One of the most dramatic climate records comes from sediment cores drilled from the ocean floor. These cores contain layer upon layer of sediment, each layer representing thousands of years. Within these layers are the shells of tiny foraminifera, those microscopic organisms we mentioned earlier. The chemistry of these shells is incredibly revealing. The ratio of different oxygen isotopes in the shell tells us the temperature of the water when the organism was alive. Cold water and warm water have slightly different isotopic signatures, and this difference gets locked into the shell. By analyzing thousands of these tiny shells from different layers in a sediment core, scientists can reconstruct ocean temperatures going back millions of years. They can see ice ages coming and going, can see periods of rapid warming and periods of gradual cooling. It's like having a thermometer that recorded temperatures for millions of years. Ice cores provide even more detailed climate records, though they go back only about 1 million years, compared to the hundreds of millions covered by ocean sediments. When snow falls and compacts into ice, it traps tiny bubbles of air. Those bubbles are samples of the ancient atmosphere. Scientists can extract these bubbles and analyze them, measuring how much carbon dioxide, methane, and other greenhouse gases were in the air when that snow fell. The results are stunning. Ice cores from Antarctica show a clear pattern. During ice ages, atmospheric carbon dioxide was lower. During warmer periods, it was higher. The correlation isn't perfect, and the causes are complex. But the pattern is clear. Earth's climate and its atmospheric composition are linked. And rocks, or in this case ice, remember both. Sedimentary rocks can also show climate patterns in their layers. During wetter periods, more sediment is washed into lakes and oceans, creating thicker layers. During drier periods, less sediment accumulates. Some sediment cores show regular cycles, patterns that repeat every few thousand or tens of thousands of years. These cycles match patterns in Earth's orbit around the Sun. The tilt of Earth's axis and the shape of its orbit change gradually over time in predictable cycles, and these changes affect how much sunlight reaches different parts of Earth. These orbital cycles, called Milankovitch cycles, influence climate, and their influence is recorded in sediment layers. Rocks also record dramatic climate events. Around 66 million years ago, an asteroid struck Earth near what's now Mexico's Yucatan Peninsula. The impact threw enormous amounts of dust and debris into the atmosphere, blocking sunlight and causing global cooling. Many plant species withered, the food chain collapsed, and the dinosaurs, along with about 3/4 of all species on Earth, went away. This event is recorded in rocks as a thin layer of clay enriched with iridium, an element rare on Earth's surface but common in asteroids. This layer, found around the world, marks the boundary between the Cretaceous and Paleogene periods. Below this layer, dinosaur fossils are common. Above it, they're gone entirely. It's a stark and sobering reminder that climate can change catastrophically and quickly. Studying ancient climates in rocks helps us understand how Earth's climate system works. We can see how it responded to changes in atmospheric composition, to changes in ocean circulation, to changes in the amount and distribution of sunlight. We can see that Earth's climate is sensitive, that it can change rapidly under the right conditions, and that these changes can have profound effects on life. This knowledge is more relevant now than ever. As humans add carbon dioxide and other greenhouse gases to the atmosphere at rates far faster than natural processes, we're conducting an unplanned experiment with Earth's climate. But it's not really an experiment, because we already know from rocks how Earth's climate responds to increased greenhouse gases. During periods in the past, when carbon dioxide was much higher than today, Earth was much warmer. The poles had no ice. Sea levels were hundreds of feet higher. Tropical conditions extended far into what are now temperate zones. Rocks tell us that what we're doing now, adding carbon to the atmosphere, will warm the planet. They tell us that this isn't speculation. It's based on evidence, on the records Earth itself kept over millions of years. Rocks give us context, showing us that Earth's climate is powerful, complex, and changeable. They also show us that changes in climate have always affected life on Earth, sometimes beneficially, sometimes catastrophically. In this way, rocks aren't just recording the past. They're warning us about possible futures. They're saying, this has happened before. Here's what occurred. Here's what changed. Here's what was affected. Up to us to listen. So rocks tell stories of fire, life, time, magnetism, and climate. But they're not finished yet. They also tell us how old they are, giving us an absolute sense of time that goes back billions of years. One of the most powerful tools scientists have for reading Earth's diary is the ability to determine the absolute age of rocks. For most of human history, people could tell which rocks were older than others by looking at their positions in layers, but they couldn't say how old those rocks actually were. That changed in the 20th century with the discovery of radioactivity and the development of radiometric dating. Here's how it works. Some atoms are unstable. They have too many neutrons or some other imbalance. And over time, they spontaneously change or decay into a different element. This decay happens at a predictable rate, like a clock that ticks at a perfectly steady rhythm. Each radioactive element has a half-life, the amount of time it takes for half of the atoms to decay. Some half-lives are short, just seconds or days. Others are incredibly long, billions of years. When rocks form, they sometimes contain small amounts of radioactive elements. Once the rock solidifies, the radioactive clock starts ticking. The radioactive atoms begin to decay, transforming into different, stable atoms called daughter products. By measuring how much of the original radioactive element remains and how much has decayed into the daughter product, scientists can calculate how long the clock has been ticking. They can determine the age of the rock. Different radioactive elements are useful for dating different types of rocks and different time periods. For relatively young materials, like things that lived within the last 50,000 years, carbon-14 is used. Carbon-14 is a radioactive form of carbon that's constantly being created in the atmosphere. Living things take it in while they're alive, but once they perish, they stop taking in new carbon, and the carbon-14 they have begins to decay. Its half-life is about 5,730 years. By measuring how much carbon-14 is left in ancient wood, bone, or other organic material, scientists can determine when that organism passed away. For older rocks, different radioactive elements are used. Potassium-40 decays into argon-40 with a half-life of about 1.3 billion years. This method is good for dating volcanic rocks. Uranium-238 decays into lead-206 with a half-life of about 4.5 billion years, making it useful for dating some of the oldest rocks on Earth. Rubidium-87 decays into strontium-87 with a half-life of about 47 billion years, useful for rocks of all ages. The beauty of radiometric dating is its precision. When multiple dating methods are used on the same rock, and they all give similar ages, scientists can be very confident in the results. It's like having multiple clocks all showing the same time. And when radiometric dates from different rocks fit together into a coherent timeline, it creates a powerful confirmation of Earth's history. Using these methods, scientists have dated the oldest rocks on Earth to about 4 billion years old. They've dated meteorites, rocks from space that fell to Earth, to about 4.6 billion years old, which matches the age of the solar system calculated from other evidence. They've dated fossils, determining exactly when different species lived and went away. They've dated volcanic eruptions, ice ages, mountain building events, all with remarkable accuracy. Think about what this means. We can hold a rock and say with confidence that it formed 200 million years ago. We can look at a fossil and know that the creature it represents lived 150 million years ago. We can examine ancient shorelines and determine that they formed 50 million years ago when sea levels were higher. This ability to put absolute dates on Earth's history transforms geology from a qualitative science to a quantitative one. It lets us build detailed timelines, understand the rates at which geological processes occur, and see patterns that span millions of years. The atoms in rocks really are like clocks, ticking slowly and steadily, counting down the eons. And the remarkable thing is that these atomic clocks can't be reset or tampered with. Once a rock forms, the clock starts, and it keeps perfect time no matter what happens to the rock afterward. It can be buried, eroded, heated, moved across the globe, but the radioactive atoms keep decaying at their constant rate. This gives us a window into deep time. We often struggle to comprehend thousands of years, let alone millions or billions. But radiometric dating makes those vast spans tangible. When we say a rock is 500 million years old, we're not guessing. We're reading its atomic clock. We're letting the rock tell us its age in a language written by the fundamental forces of physics. Radiometric dating has revolutionized our understanding of Earth. It's confirmed that Earth is incredibly old, far older than people once believed. It's shown that life has existed for most of Earth's history, going back at least 3.5 billion years. It's revealed the timing of mass extinctions, the ages of ancient civilizations, and the pace of evolutionary change. It's one of the most powerful tools we have for understanding our planet's past, and it's all thanks to the slow, steady ticking of atomic clocks preserved in rocks. But rocks still have more surprises. Some of them don't just tell stories with their chemistry and structure. Some of them glow, shine, and even generate electricity under the right conditions. Let's explore some of the more magical properties of certain rocks and minerals. Now we come to something truly enchanting. Some rocks, under certain conditions, do things that seem almost magical. They glow under invisible light. They produce electricity when squeezed. They hold properties that make them not just historical records, but also materials with fascinating physical behaviors. Let's start with fluorescence. Certain minerals, when exposed to ultraviolet light, a form of light beyond what our eyes can see, begin to glow in brilliant colors. Under normal light, these minerals might look ordinary, perhaps gray or brown or white. But turn on a UV lamp in a dark room, and suddenly they burst into vibrant greens, reds, blues, yellows, oranges. It's like the rocks have a hidden rainbow inside them that only shows up under special circumstances. What's happening is this. The UV light carries energy. When it strikes certain minerals, that energy excites electrons in the mineral's atoms. These excited electrons jump to higher energy levels. But they can't stay there. They quickly fall back to their normal levels, and as they do, they release the extra energy as visible light. This glow is the fluorescence. Not all minerals fluoresce, only certain ones with specific chemical impurities. Calcite sometimes fluoresces in reds or blues. Fluorite, which gave fluorescence its name, often glows blue or purple. Willemite, a zinc mineral, can glow bright green. Scheelite, a tungsten mineral, fluoresces bright blue, which is so distinctive that miners used to carry UV lamps at night to find scheelite deposits in the dark. They'd shine their lamps on rocks, and the scheelite would light up like a beacon. Aragonite can fluoresce in beautiful greens or blues. Some agates glow yellow or green. Certain opals glow bright green, almost like they're lit from within. The colors are often stunning, turning ordinary-looking rocks into glowing works of natural art. Collectors prize fluorescent minerals, displaying them under UV lamps to show off their hidden beauty. What makes a mineral fluorescent is often the presence of trace elements, tiny amounts of impurities that got mixed into the mineral when it formed. These activators, as they're called, are what allow the electrons to absorb and release energy in just the right way to produce visible light. Pure calcite doesn't fluoresce much, but calcite with a tiny bit of manganese might fluoresce red. Calcite with a little lead might fluoresce yellow. It's these small differences that create the spectacular variety of fluorescent colors. Fluorescence is more than just pretty. It's also a tool. Geologists use UV lamps to identify certain minerals in the field. Oil prospectors use fluorescence to find petroleum deposits because some organic compounds fluoresce. Archaeologists use UV light to examine ancient artifacts, revealing details invisible to the naked eye. Fluorescence connects the invisible world of UV light with the visible world our eyes can see. And it reminds us that rocks aren't just static objects. They interact with light in complex and beautiful ways. But fluorescence isn't the only remarkable property some minerals have. There's also piezoelectricity. Certain minerals, when you squeeze or strike them, generate an electric voltage. Conversely, if you apply an electric voltage to them, these minerals, they change shape slightly. This property is called piezoelectricity, from Greek words meaning pressure and electricity. Quartz is the most famous piezoelectric mineral. Pure quartz crystals, when compressed, produce a small electrical charge. This property is used in all sorts of technology. Quartz watches use tiny quartz crystals. An electric current makes the quartz vibrate at a precise frequency, and that vibration keeps the time. Quartz is also used in microphones, speakers, and sensors. The piezoelectric property of quartz makes it incredibly useful in modern electronics. But piezoelectricity isn't just useful. It's also a reminder that rocks aren't inert. They respond to pressure with electricity. They respond to electricity with movement. They're dynamic in ways we don't usually notice. Every time you press a quartz button or use a device with a quartz component, you're relying on a property that rocks have had for billions of years, waiting for humans to discover and use it. There's also thermoluminescence, where certain minerals glow when heated. If you heat them to a few hundred degrees, they release stored energy as light. This happens because radiation from radioactive elements in the surrounding rock has been exciting electrons in the mineral over thousands or millions of years. These electrons get trapped in imperfections in the crystal structure. When you heat the mineral, the electrons escape and release their stored energy as light. The amount of light released can tell scientists how long the mineral has been buried, making thermoluminescence useful for dating ancient pottery and sediments. Some minerals are even magnetic naturally. Magnetite, an iron oxide, is naturally magnetic. Ancient people discovered this and used magnetite to make the first compasses. Lodestone, a naturally magnetized form of magnetite, was used for navigation long before anyone understood why it worked. The rock itself was pointing the way, responding to Earth's magnetic field, guiding travelers across oceans and deserts. And then there are minerals with perfect cleavage, meaning they break along flat plains, creating smooth, mirror-like surfaces. Mica is famous for this. You can split mica into sheets so thin they're almost transparent, yet each sheet is perfectly smooth. Ancient people used mica as windows. Today, it's used in electronics and cosmetics. The way mica cleaves is a direct result of its crystal structure, the way its atoms are bonded in layers. Each of these properties, fluorescence, piezoelectricity, thermoluminescence, magnetism, cleavage, they all come from the internal structure of the minerals, from how their atoms are arranged and bonded. And they remind us that rocks and minerals aren't just passive recorders of history. They have active properties. They interact with light, electricity, heat, and magnetic fields. They're participants in the physical world, not just witnesses to it. When you hold a piece of fluorescent calcite and watch it glow under a UV lamp, or when you feel the subtle tingle of electricity from a squeezed quartz crystal, you're experiencing something that connects the world of rocks with the world of energy and light. You're seeing that minerals are bridges between the solid and the ephemeral, between matter and forces. And it adds another layer to the stories rocks tell. Not just here's what happened, but here's what I can do. These properties also remind us that science is full of wonder, that the natural world is constantly surprising us with its complexity and beauty, that even something as ordinary as a rock can hide extraordinary behaviors waiting to be discovered. So now we've journeyed through igneous, sedimentary, and metamorphic rocks. We've seen fossils, time markers, magnetic records, climate archives, atomic clocks, and glowing minerals. We've explored how rocks are created, changed, broken down, and reformed in the great cycle that shapes Earth's surface. But now, as we come to the end of our journey, let's step back and think about what all of this means. Every rock you've ever seen or touched has a story. That pebble on the beach, smooth and round from being tumbled by waves for perhaps thousands of years. The gravel in your driveway, pieces of larger rocks broken down and transported by glaciers or rivers. The granite in monuments and buildings, formed miles underground and now exposed to the sky. The fossils in museums, remnants of life from unimaginable ages past. When you realize this, when you truly understand that rocks are records of Earth's history, the ground beneath your feet becomes less ordinary. A walk in the park becomes a walk through time. A hike in the mountains becomes a journey to ancient continents that collided to push those mountains skyward. A visit to a limestone quarry becomes a trip to an ancient seafloor, where countless organisms lived and passed away, building reefs and leaving their shells behind. Rocks teach us humility. They remind us that Earth existed for billions of years before humans appeared, that countless processes shaped this planet long before we were here to witness them. A rock that formed 100 million years ago has existed for a length of time that dwarfs all of human history. The entire span of civilization, from the first cities to today, is just a tiny fraction of that rock's existence. But rocks also teach us connection. The carbon in your body might once have been part of an ancient organism that became a fossil, then was released back into the air or water through erosion, then was absorbed by a plant, then eaten by an animal, and eventually made its way into you. The oxygen you breathe was released by ancient photosynthetic organisms, some of whose fossilized remains are now in rocks. The iron in your red cells might have cycled through multiple rock types over billions of years. We are not separate from the rock cycle. We are part of it. Rocks also teach us resilience. They show us that Earth has survived tremendous changes. 5 major mass extinctions where most of life went away. Snowball Earth periods when ice covered almost the entire planet. Hothouse periods when there was no ice at all. Asteroid impacts, supervolcano eruptions. And through it all, life persisted, adapted, and eventually thrived again. Earth has been through catastrophes we can barely imagine, and it recovered each time, though the recovery sometimes took millions of years. This perspective can be comforting. It shows us that Earth is incredibly resilient, that its systems, while complex, have endured through enormous changes. It also shows us that we're part of a much larger story, that our individual lives and even our species' existence are brief moments in a vast narrative. But rocks also teach us responsibility. They show us that Earth systems are interconnected, that changes in climate affect what rocks form and where, that mass extinctions leave permanent marks in the fossil record, that rapid changes can have profound and long-lasting effects. And while Earth has always recovered from past catastrophes, those recoveries took millions of years. That's much longer than human civilization has existed. When you hold a stone, you're holding a piece of Earth's memory. That stone might be older than mountains. It might be older than the Atlantic Ocean. It might be older than flowering plants or dinosaurs, or even complex life. Some rocks on Earth are over 4 billion years old, nearly as old as the planet itself. They've witnessed almost the entire history of our world. Imagine that for a moment. A stone that formed when Earth was still young, when the moon was closer and the days were shorter, when the atmosphere was toxic to us, but perfect for the earliest life forms. That stone has sat through ice ages and warm periods, through the rise and decline of countless species, through the formation and breaking of supercontinents. It has been a silent witness to billions of years of change, and it still exists today, unchanged in its essential nature, waiting for you to find it and wonder about its story. Rocks connect us to deep time, to the almost incomprehensible ages that came before us. They make the abstract concept of millions and billions of years tangible. You can hold it, touch it, see its layers and crystals and fossils. It's real, and its story is real. And by learning to read that story, we become time travelers of a sort, journeying backward through epochs and eras, seeing worlds that no longer exist except in the records preserved in stone. So the next time you see a rock, pause for a moment. Look at it more closely. Notice its color, its texture, whether it has visible crystals or layers. Wonder where it came from. Was it made from fire or from the slow accumulation of sediment? Has it been changed by heat and pressure? What has it seen? What stories does it hold? You might not be able to answer all these questions, but asking them changes how you see the world. It turns every stone into a mystery, every cliff into a library, every mountain into an archive of Earth's deep past. We often think of history as something written in books, as dates and events that we learn about and memorize. But the oldest and most complete history isn't in any library. It's beneath your feet, all around you, in the stones that pave roads and build walls and rest quietly in fields and forests. Earth's diary is everywhere, written in a language of minerals and layers and fossils and magnetic patterns. And once you learn even a little of that language, you never see rocks the same way again. So, as you lie here, comfortable and calm, perhaps thinking about all we've explored tonight, remember that you're resting on a planet that has been keeping a diary for over 4 billion years. Every stone is a page, every mountain is a chapter, and you, reading this now or listening to these words, you're part of the ongoing story. You're a tiny moment in Earth's vast narrative, but you're here. You're part of it. And the rocks that came before you will still be here long after, continuing to record, continuing to remember. Let that thought settle gently over you. You don't need to understand every detail of geology to appreciate the wonder of it. You don't need to memorize the names of every rock type or the dates of every epoch. You just need to know that Earth has a history, a long and incredible history, and that it's written in stone. And that every rock you've ever seen is a page from that history, patiently waiting for someone to read it, to wonder about it, to connect with the deep time it represents. In a way, rocks are the ultimate storytellers. They don't embellish or forget. They don't change their stories based on who's listening. They simply exist, holding their secrets, preserving their memories, waiting with infinite patience for someone curious enough to ask what they've seen. And now, as we near the end of our journey, take a moment to feel grateful for the ground beneath you. Whether you're lying in bed, sitting on a couch, or resting somewhere else, you're supported by Earth itself, by stones and soil that have been here far longer than you and will be here far longer still. Those stones have held up mountains and cradled oceans. They've witnessed the rise and flourishing of life, the coming and going of countless species. They've been sculpted by wind and water, heated by fire, transformed by pressure. Think about the journey of a single grain of sand. Perhaps it began as part of a granite mountain, formed deep underground from cooling magma millions of years ago. That mountain was slowly pushed upward by tectonic forces, rising into the sky over millions of years. Wind and rain began to wear it down. Freeze and thaw cycles cracked the granite. A tiny piece broke off, perhaps no bigger than your fingernail. That piece tumbled down the mountainside in a rock slide. It landed in a stream where flowing water carried it downstream. The water tumbled it against other rocks, slowly grinding it down, making it smaller and rounder. It traveled for miles, maybe hundreds of miles, over thousands of years. Eventually, it reached the ocean. In the ocean, waves tossed it back and forth. It became even smaller, eventually just a single grain of sand. That grain settled on the seafloor, along with billions of other grains. Slowly, layer upon layer of sand accumulated. The weight pressed down. Minerals in the water cemented the grains together. Over millions of years, the loose sand became sandstone, solid rock once again. But the story didn't end there. Tectonic forces pushed that seafloor upward. The sandstone that had been underwater was now on dry land, perhaps in a desert. Wind and water began to erode it again. Our grain of sand was freed from the sandstone. It blew across the desert in a sandstorm. It settled in a new location. Perhaps it's still there now, waiting for the next chapter of its journey. This is the story of just one grain of sand, but it's a story that plays out for every particle, every atom in Earth's crust. Nothing is permanent in its form. Everything is constantly being recycled, transformed, moved, and changed. The rock cycle is endlessly turning, and every rock, every mineral, every grain of sand is part of that great cycle. When you understand this, you realize that rocks aren't dead things. They're not static and unchanging. They're participants in Earth's great dance of transformation. They're being created, destroyed, and recreated constantly, though on timescales so vast that they seem permanent to us. A rock that looks solid and eternal to you might be in the middle of a transformation that will take another 10 million years to complete. This perspective changes how we see permanence and change. Nothing lasts forever in its current form, not even mountains, not even continents. Everything flows, everything changes. Everything is part of a larger cycle. And yet, the matter itself continues. The atoms in that grain of sand might have been part of a dozen different rocks over the past billion years, but they're still here, still part of Earth, still participating in the story. There's something almost comforting in that. It means that nothing is truly lost. Everything is transformed, recycled, renewed. The rocks beneath you might have been ocean floor, mountain peaks, and river sediment at different times in their long history. They've been many things, and there'll be many more things in the future. They're not at the end of their story, they're in the middle of it. Just like you are in the middle of your story. And now they're here, holding you, supporting you. Part of the vast and ancient rock cycle that never stops turning. You're not separate from this cycle. You're part of it. The calcium in your bones came from somewhere, perhaps from limestone that formed in an ancient sea. The iron in your cells came from somewhere, perhaps from rocks that rusted and released their iron into soil and water. You are made from the earth, and one day you'll return to it. And the atoms that make up your body will continue in the cycle, becoming part of rocks and water and life again. That's the ultimate story rocks tell. That everything is connected, that nothing is truly lost. That Earth is a closed system where matter is endlessly recycled, transformed, and renewed. Stars exploded billions of years ago, and their atoms became part of the cloud that formed our solar system. Those atoms became part of Earth, part of its rocks, part of its water, part of its life. And those same atoms are here now, part of you, part of everything around you. So rest easy, knowing that you're part of an ancient story, one that began long before you and will continue long after. The rocks remember, Earth remembers, and the story they tell is one of transformation, resilience, and endless cycles of change. A story written in stone, waiting to be read by anyone who takes the time to look, to wonder, to appreciate the vast history held in every pebble, every cliff, every grain of sand. Thank you for joining me on this quiet journey through Earth's diary. Whether you're still awake, drifting off, or already dreaming, I hope you found something here that brings you peace, curiosity, or simply a new way of seeing the world around you. The rocks will still be here tomorrow, and the next day, and for millions of years to come, patiently holding their stories, waiting for the next curious mind to discover them. From the sleepy library, good night. Rest well, dream deeply, and remember that you're standing, sitting, lying on billions of years of history. Every stone you step on is a silent witness to the incredible journey of our planet. You are part of that journey. You always have been. Sweet dreams.